Assalamualaikum and a very good day. We are from Group 2 and will present about the structure of zinc blende, or also known as fluoride. Our group consists of 5 members, which are me, Nurul Atirah binti Yusni, Nur Arifah binti Muhammad Kamal, Muhammad Ashraf bin Muhammad Hafiz, Nur Ayuni Umairah binti Kamaruddin, and Nur Ain Syamilah binti Kamal Arifin. Our presentation will be divided into 6 parts. The first one is unit cell and lattice type that will be presented by me. Next, Nur Arifah will present about the unit formula and the 2D plane view. Then, we'll continue with Muhammad Ashraf, who will explain about the locations of atom. Next, Nur Ayuni Umairah will explain about the coordination number, and the last presenter, Nur Ain Syamilah, will present about the applications of zinc blende. Now, I will proceed to the first part of this presentation, which is the unit cell and lattice type. Unit cell of a crystal is an imaginary parallel-sided region from which the entire crystal can be built up. So, what is the unit cell and the lattice type of zinc blende? Zinc blende has a face-centered cubic unit cell of zinc 2+ and S2-. This is because the sulfur ion builds the lattice at each corner and face center of the unit cell. So, if you can see from the figure here, each side of zinc blende structure has equal length, which is A equal to B and equal to C. In addition, the angles of alpha, beta and gamma are equal to 90 degrees. Alpha is the angle between the line A and B. Beta is the angle between A and C, while gamma is the angle between B and C. Furthermore, as zinc blende is a cubic close-packed lattice type, it has the stacking of ABC, ABC, ABC as shown in the figure here. The third layer lies in alternative indentations and making it staggered to both previous layers. Next, I will pass to Nur Arifah to explain about the unit formula and the 2D plane view.
Thank you, Atira. Now, I will proceed to this presentation with the unit formula of zinc blende structure. So first, let's take a look at the calculation of the number of atoms in a unit cell of zinc blende. I will start with the anion, which is sulfur, the blue one in the picture. As mentioned by Atira earlier, the S2- build the lattice at the corners and also at the faces of the unit cell. The corner atoms contribute only 1/8 to a unit cell, as they are being shared with another 8 unit cells. Meanwhile, the atoms located at each face contribute only half for a unit cell, since it is shared between 2 unit cells. So, from the calculation shown in the slide, the number of sulfur atoms is 1/8 times 8 corners, which is equals to 1, plus with 1/2 times 6 faces, which is equals to 3. Thus, this results in the total of 4 sulfur atoms in a unit cell of zinc blende, in which the corner atoms contribute 1, while the face atoms contribute 3. Next, for the cation Zn2+, which is the orange one in the picture, it has 4 atoms in a unit cell of zinc blende. This is because the zinc atoms fill in only half of the total tetrahedral holes in the unit cell, which is located at each octet of a unit cell. Half means that it only fills 4 out of 8 holes in the unit cell. So the calculation performed just now is consistent with the chemical formula of zinc blende, which is Zn(S), as the ratio of cation and anion is 1:1. Now that we are done with the unit formula of zinc blende, let us move to the next section that will be presented by Ayuni.
Now, I will continue presentation on this topic. So for my part, I will focus on the location of each atom, and to show you clearly on which position is each of the atom exactly located, I will draw on the structure as shown in the slide. As mentioned earlier, sphalerite is contained of 2 atoms, which are zinc and sulfur. So firstly, I will show you guys the location of the anions, which is sulfur. Basically, these sulfur are located at the face and the corner of this cubic closed pack. As you can see here, there are 8 lattice points located at the corner. So here is 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and also there are 6 other lattice points located at the face of this cubic, which is here 1, 2, 3, 4, 5, and 6. From all of this sulfur here, we can also see that all of them are touching each other along the face diagonally. Done with the anion part, now we take a look at the location of the cations, which is zinc. So for zinc, it is quite complicated to make you understand on which exact position does this cation located if you cannot imagine clearly the whole structure of cubic closed pack. But don't worry, I will try to help you to understand on this part. So from the face-centered cubic of all this sulfur that I have shown just now, it is actually containing 8 tetrahedral holes, in which it does have at every 8 octants of the cube, which is here 1, 2, 3, 4, 5, 6, 7, and 8. However, as you can see, the zinc ion only occupy 4 out of these 8 holes, which is alternately to each other. So you can see there, the zinc ions are colored with purple. I think I have done with my part, so that is all that I can explain about this part. I will pass the presentation to the next presenter.
Now, let's proceed to the next part of this presentation, which is coordination number. Coordination number is actually atoms that are coordinate to a particular atom in a unit cell, or it also known as the nearest neighboring atom. By referring to this 3D structure, the yellow color represent as sulfide ions, which are face-centered, while the blue colors represent as zinc ions, which are alternate tetrahedral voids. So, how do we know it was alternate tetrahedral voids? It was by referring to its plan view. Okay, so now focus on the black color, which are the coordination 1/4, 3/4, 3/4, and 1/4. So it proved that it was in alternate arrangement. Next, coordination number also we can prove by calculation. This calculation we get it from Inorganic Chemistry textbook 5th edition. It was written as ionic radius of zinc ion is 74 picometer, while ionic radius for sulfide ion is 184 picometer. So the ratio of these two values is 0.402. So as we know, the range of ionic radius for octahedral voids is 0.414. So as this value is lower than 0.414, this suggests a tetrahedral arrangement. His ion is surrounded by 4 neighbors, so the structure has 4 coordination. So that's all from me. I will pass to the next presenter.
Thank you, Ayuni. Okay, now I will proceed the presentation with the application of zinc blend structure. So here are the examples of zinc blend application. Firstly, zinc blend or zinc sulfide is used in optical material. Zinc sulfide grown by chemical vapor deposition (CVD) at 2 until 6 infrared exhibit exceptional fracture strength and hardness, which lead to its frequent choice for military applications or other harsh environments. This material is often used in the 8 to 12 mm region, and its high resistance to rain erosion, high speed dust, and particulate abrasions makes it suitable for exterior IR windows on aircraft frames. Next, it is used in cosmetics. Phosphorescent non-toxic zinc sulfide makes it ideal for use in glow-in-the-dark cosmetics. The US Food and Drug Administration approved it for this use in 2000. According to FDA, it's the only luminescent color approved for cosmetic use, and of course, it's not for everyday and not for near your eyes. You can recognize it by its whitish, yellowish, greenish glow. Other than that, zinc sulfide is used as a pigment. In nature, both zinc sulfide polymorphs usually contain significant amounts of iron that makes them appear black. The purified salts are white to pale yellow or grey. The most common use of zinc sulfide is as a pigment for paints, plastic, and rubber. For your information, lithophane, a mixture of zinc sulfide and barium sulfate, is a widely used pigment for low gloss paints. Lastly, zinc sulfide is used in electronic and decorative materials. This is because zinc sulfide is phosphorescent, which makes it useful for several electronic and decorative applications. Among its earlier uses were X-ray, television screens, cloth, and wash dyes. In this age of nanotechnology, zinc sulfide frequently forms the shell of semiconductor potted dots with cadmium selenide as the cores. So that's all from our group. Thank you.